we might move on to the final presentation today, which, for better or worse, is myself. Let me see, where am I? Need to do that. Okay, so yes, I stepped into this last time slot today because the original presenter, Jeff Byron, found himself in in Norfolk Island, isolating with COVID without his computer. So Jeff will be speaking in the last session in 2 weeks' time, and I've dragged out a presentation that I gave to the Astronomical Association of Queensland back in July. So some of you guys will already have seen most of the content in this presentation. I apologise for the repetition, but it should still be entertaining, hopefully. So David's going to run the slides for me like he did with Stan, because although I'm not too far from civilization, my internet connection is atrocious. So I think the simplest thing is for David to progress the slides for me, and I'll hopefully be able to see the slides myself. Where are we?
Mark, I'm on the outline now.
Okay, all I see is your desktop. It might update soon, but in the meantime, what I might do is just get the PowerPoint up on my screen and talk to it. So we're on the front page, the Eclipsing Binaries exhibiting period change. Is that right?
Hang on, we can be. We are on that page now.
Okay, so any of you who might have seen presentations I've given in the past will recognise that background.
I can't. I'm just getting a black screen.
Yeah, so am I.
Right.
It looks like a desktop.
Yes,
Okay.
that's what I'm getting to. Okay.
I will restart sharing then.
Yeah, yeah. I'll stop now.
Is that better?
That's good.
That's got it. That's good.
Yeah,
Thanks.
that's good. Thank you.
Excellent. Yep, I can see that.
Oh, good.
Get rid of that. Okay. Yes. So that background image there is a photo from the Astronomical Society of New South Wales's Bowen Mountain Observatory, and to me, that just has so much potential for a great observing night. So anyway, that's a personal thing. I'm going to start with the outline slide. So David, if you could progress. First of all, I'll briefly describe my observatory and list the aims of the Southern Eclipsing Binaries project that is within the Variable Stars South program. I'll introduce the concept of the observed minus calculated diagram, which is used extensively throughout this talk. And then I'll give a few examples and hopefully inspire some people to take up this sort of work as well. So next slide, David. So this is an observatory myself and a mate built back in 2017. Congarini is a little community, scattered houses about halfway between Brisbane and Sydney, quite close to the coast, about 15 kilometres, at an elevation of 20 metres if we're lucky. So the seeing can be extremely good, but other times the fog is a problem. The nearest town is about 7 kilometres to the east. The skies are dark. We run an Airbnb accommodation here as well, and whenever I get a chance, I'll show the guests, the moon and planets and the brighter deep sky objects, and they all are quite impressed with it all, I think. So the pier on the left, as you see it there, this is an old photo. The pier now carries a Skywatcher mount with that 8-inch Schmidt-Cassegrain telescope and side-by-side mounted 80mm refractor. The Schmidt-Cassegrain is used for visual deep sky observing only, but the refractor has CCD cameras and filter wheels for photometry of stars brighter than about 10th magnitude. Okay, I can go fainter, but that requires longer exposures. So for fainter stars, I use the telescope on the right-hand pier, which is a 14-inch Ritchie-Creation telescope from Bintel, which is for those of you not in Australia, that's a commercial astronomy supplier in Sydney. The mount is a Paramount MX Plus. There's a S-Big CCD camera and filter wheel and all the bells and whistles, and it's been sitting idle for the last 12 months because the mount isn't working, and I'm having all sorts of hassles getting adequate help from the software BISC people. Anyway, that's something we will sort out. Okay, so for stars very bright, but too bright for the 80mm refractor, I can take the S-Big camera and put a 200mm camera lens on, the same lens that Roy just described in his talk. I've got exactly the same camera lens. And so for stars, brighter than about 4th magnitude, I use that. All my work nowadays is with CCD cameras. I did start off, spent 8 years or so doing DSLR photometry, but I've moved to CCDs about 5 years ago. There's nothing wrong with the DSLRs, but I find the work with the CCD cameras is just a little bit more accepted by people. On to the next slide, please, David. All right, the project within Variable Stars South that I'm going to be talking about is the Southern Eclipsing Binaries project, or SEB. Variable Stars South has been running eclipsing binary projects in various forms for over a decade now, and the current project has the following goals, basically. So essentially, we want to determine accurate epochs, which is essentially measure the time of minimum of the primary and secondary eclipses, and we want to determine accurate periods for the orbital period of the binary. We want to identify EBs that are exhibiting variations in their orbital periods, and there are a number of reasons why that might happen, and I'll go into detail and give examples throughout this talk. We want to determine what those causes are if we can, and one of our major goals is to publish annual lists of eclipse timings so that other researchers around the world can use our data as well. For individual systems showing interesting behaviour, we'd like to publish a detailed analysis, and that's where collaborations with professionals like Ed come into play, because they have the understanding and the background and basically the opportunity to do spectroscopy on some of these systems as well, which adds so much more information to the analysis. Eclipsing binaries are a very active field for professional and amateur astronomers. Last year alone, I just did a quick search online, there were over 500 journal papers relating to EBs last year. In the southern hemisphere, they're relatively under-observed compared to the northern hemisphere, mainly because there are reverse that. The northern hemisphere has so many more observers, and have been doing so for a lot longer. So down south here, we have the opportunity to make some very exciting discoveries. It's just a matter of observing and analysing. So far within this, sorry, David. So far within this project, we have measured over 1,100 times of minimum from over 200 different targets within the project, and that is increasing year by year. Okay, David, on to the next one. So quickly, I'll explain what we do and what we're looking for. This is a light curve I recorded a couple of years over several nights, a couple of years ago over several nights. We've folded them into a phased light curve so that we can see the whole light curve. We have the deeper eclipses are the primaries, the shallower one are the secondary eclipses. I've folded this light curve using the epoch and period listed in the AAVSO's variable star index, and those values are given at the top of the page there. We can see, I mean, if the period and the epoch were exactly right, the primary eclipse would occur at phase 0, and the secondary for VV Ori in particular would occur at phase 0.5. Now that's clearly not the case. They've occurred a little bit earlier than we would expect. And in the case of VV Orionis, it's probably because the period listed in the VSX, the variable star index, is just very slightly shorter, or sorry, longer than it truly is. So one of our aims with the project is to correct those period values for the various targets so we can predict future eclipses more accurately. Let me see. Just as a just for reference, I'll be referring to the period and epoch of a particular star as the light element, so that those two values are referred to as a light element. So when I say light elements, that's what I'm referring to, the period and epoch. It's the variations from the predicted eclipse times that we're interested in. That's the main thing. What I do to determine the time of the minimum is to use that program that Ed mentioned, Paranzo, to fit a polynomial, usually of order 4 or 6, depending on the complexity of the shape. Jeff Byron, when he gives his talk in 2 weeks, will describe a much more sophisticated method and give the reasons for going to that extent. But I'll leave that to Jeff to explain. Okay, next slide, please. So the tool I'm using is called an observed minus calculated diagram. Basically, it's a plot on the y-axis of the difference between when we observe an eclipse and when we've calculated that eclipse to have occurred. So if the two agree, there will be a value of 0. If there's a big difference between it, like if it occurs 2 hours early or something, then it'll be a high value on the curve. To predict our eclipses, we use that equation towards the lower half of the slide. The calculated time is equal to the 0 epoch, which is generally an earlier observed eclipse, a primary eclipse, plus the period that we think the star has times the cycle number. Cycle number is basically just the number of orbits that have occurred since the zero epoch. Now, to get those zero epoch and period, or the light elements, as I mentioned, we can use the General Catalogue of Variable Stars or the AAVSO's Variable Star Index. They're the two main sources that I use. There are publications, also papers that you can refer to that might have different values, but the GCVS and the VSX are my main sources. Unfortunately, or fortunately, because it makes our life more interesting, those catalogues do contain inaccuracies, some much worse than others, and we wish to essentially correct those inaccuracies, or at least improve them. Next slide, please. So this is a theoretical observed minus calculated diagram of a star that has a perfectly constant period, and we know that period perfectly. So what we end up with is that blue line along the zero of the y-axis. And if that's what we saw in every star, there'd be no point observing them because we know them perfectly. But in fact, that's hardly ever the case. So if we have the next slide, David, this is what we would expect to see if the period was constant, but slightly different to what we thought. So in this case, the period is a little bit longer than what we thought it was. The eclipses occur slightly a lot further and further away from the predicted time as we go further into the future. And I've found quite a few examples of this in the targets in the SEB project. If the assumed period was slightly too long, the curve would slope downwards. Next slide. Okay, now this is actual data from a southern variable star called V701 Centauri. The period is about 3/4 of a day. The time on that leftmost data point, blue data point, 1996, is the time when the epoch in the variable star index was measured. So that's some 60 odd years, 55 years in the past. What we can see from this diagram is that the period that is in the VSX is very slightly shorter than what the true period is. Each blue dot represents either a primary or secondary eclipse that was measured, and the ones on the very right-hand side, the few dots up there, were made by myself and Neil Butterworth. There is also an eclipse in there that was observed by the TESS satellite that has been taking extremely nice light curves for the last 4 or 5 years, I guess. Now, one of the eclipses that Neil observed was actually recorded by the TESS satellite at the same time. So they were perfectly identical eclipse. The difference measured from the TESS satellite data and from Neil's data was only 13 seconds, which is within the error bars of the measurements usually. So in this respect, Neil's inexpensive DSLR photometry setup did as well as NASA's $200 million satellite. But the satellite does have other advantages. Now, I will point out that measured minima times should have realistic error estimates, but these are often missing from published data. Or if they are there, they are unrealistically small error estimates. and I'll leave it till Jeff Byron gives his talk because he will go into detail about this in 2 weeks' time. Next slide. If we take that all the data from 1966 to 2020, we can do a linear regression on that data and essentially deduce a much more accurate orbital period, replot the O-C diagram, and we get the result that we see on the screen now. So the period shown on the previous slide was 0.738447 days. On this slide, it's 0.73845032 days. So we have 2 or 3 more decimal places, and the error is in that last decimal place of 4. So we've improved the accuracy by a factor of 1,000 or so. And we can see that the difference between the period shown in the variable star index and what we've just calculated with the regression is less than 0.3 of a second per orbit. So it's a very small difference, but that accumulates over the time to be quite significant. So in the unregressed data, there was almost 2 hours difference between the predicted and the observed eclipses. Using the new regressed period, we can be very confident of predicting the eclipses well into the future to a matter of minutes at most. So what we would like to do is update the data in the VSX to reflect the actual newly regressed period. We'll have to see how we can do that. Okay, next slide, David. Another example of this sort of system where the period was slightly wrong, constant but slightly wrong, is BH Centauri. Also about 0.8 of a day period. But the original epoch listed in the VSX dated way back to 1945. So we've got 80 years worth of data almost. So the regressed period, the newly calculated regressed period, was only 0.014 second different to the one in the VSX. But it made a difference in the like it was obvious that there was a difference between the predicted and the observed times of eclipses. Note here the accuracy and the precision of the new regressed period. There's 1, 2, 3, 4, 5, 6, 7, 8. It's accurate to the 9th decimal place, which is incredibly precise. So there we have 2 examples of eclipsing binaries where the period was constant but slightly wrong in the databases, and we've been able to improve those. But what would happen if the period was actually increasing or decreasing? So David, if you could have the next slide. In the case of a period that is slowly increasing with each orbit, we would see a upwardly curving parabola. A downward parabola would indicate a decreasing orbital period. And the reasons for the period to be changing are thought to be caused by transfer of momentum between the 2 stars, either due to mass flow, like Ed explained in his talk earlier on today, or some sort of magnetic coupling between the 2 stars. Now, I'm not going to go into any details because I don't know them. But we've found quite a few examples of these sorts of changing periods. So David, next slide, please. This is the star RA. It's got quite a long period, 4.4 days compared to what I normally look at, because these long period ones take much longer to record the light curves. But the observations of this star go back to 1894, and we can see that the period has been steadily increasing ever since then. My measurement in 2018 on the right-hand side coincided precisely with a measurement by one of our VSS members, David Blaine, in South Africa. So we both measured essentially the same difference between the observed and the calculated eclipse time. Next slide, please. This is another star, BO Indus, much shorter period, which is easy to work with, only 0.4 of a day. In this case, the orbital period has been steadily decreasing since it was discovered in 1991. My measurements over there at 2019 line up pretty nicely with the other data points. I made further measurements in 2021 and used TESS archival photometry to measure an eclipse in 2020. When I plotted them onto the A-C diagram, David, next slide, they didn't fall on that parabola at all. They were offset by hours, many hours. And this confused me for a while until I realised what was going on. The period didn't just suddenly jump between 1919 and 2020. What we're seeing here is a miscalculation of the cycle number, the number of orbits between when the zero epoch was in 1991 and the current eclipse. What's happened is that the equation used in Excel to calculate the cycle number mistakenly identified primary eclipses as secondaries and vice versa, and this resulted in a jump equal to half the orbital period, or in the case of BO Indus, that's about 0.2 of a day. So if we could have the next slide, David. This is a theoretical diagram showing what's happened. So we have a period decreasing by only a very, very small amount per day, but over time that accumulates to 1/4 of the period, and then suddenly the cycle count steps up, and a mistake is made in the calculation of the cycle count, and so we get that big step up, and then it starts to curve back down again. And this step always occurs at 1/4 of the period of the orbit. If we recognise that this cycle count error has occurred, then we can make a simple correction, as shown in the next slide, David, where my data points now line up pretty well with the general parabolic curve. Now, we have another example. Our next slide, David, looks a complete and utter mess. And it took me some time to work out what was going on. This was, in fact, the first example of cycle count errors that I came across, not that simple one in the previous example with BO Indus. RV Grusis showed this sort of O-C diagram, and eventually I worked out what was going on. The orbital period here is only 1/4 of a day, so even shorter than BO Indus, and the slightly incorrect period that was obtained from this paper here by Covino in 1998, that period was slightly incorrect. I'll show you on the next slide what the theoretical curve looks like. So here we have multiple cycle count errors occurring. So what we have to do is recognise that this is a problem and make the corrections, which I've done on the next slide. These graphs were lifted from an article I wrote for the VSS newsletter back in July last year. The data points are the same as I showed on the previous slide, but are colour-coded for the various observers. After correcting for the cycle count errors in the bottom graph, we see that all the data points line up very nicely with the parabola, which indicates that the orbital period is steadily increased, decreased. I'm not forgotten which way around it goes. But since 1952, when it was discovered, the orbital period has been changing steadily, not those jumps that the original O-C diagram seemed to indicate. Okay, if we go back to the RRA O-C diagram, we see that there is no indication of these steps at all. And the reason for that, well, let me step back. There's no cycle count errors, despite the rate of period of change in this RRA is 5 times greater than RV Grusis. So we would, initially I thought, well, we should be seeing these cycle count errors. But in fact, the period of RRA is 17 times longer than RV Grusis. So we have to wait a bit of time until we see the first of these cycle count errors. In fact, it'll probably won't happen for another 50 years or so. So I'll leave that to the next generation of observers to see. Next slide, David. Okay, so we've had examples of stars that have a constant period. We have examples of stars that have a continuously changing period. This is an example here, V625 Carinae. This star seems to have had a one-off step in the period, in the orbital period. The earlier data on the left of this diagram all fall pretty much along a horizontal line. So it tells me that the period that I used to create this O-C diagram, it's in fact one that I derived myself for those earlier data points. That period was correct. You know, it falls along the zero of the y-axis. But somewhere between the earlier data set and the later data set, the period has changed. It's for that data on the right-hand side, it's in a straight line. So that tells me that the period isn't changing over that time, but it's not the same period as the earlier data on the left-hand side. And in fact, they differ by, you know, that point 1, 2, 3, 4, 5 zeros, 3 of a day. So it's a very slight change in period, but there is a step. It didn't just continuously change, there was a big step. And if you extrapolate those two sets of data down, it looks like it had occurred somewhere around early 2012. So for some reason, the orbital period changed by about 0.3 of a second in early 2012, and I'm not entirely sure why that is. I found 2 other examples in the literature with O-C diagrams like this. Another star in Centaurus, V752 Centauri, and YY Corona Borealis. I haven't seen a definitive reason why a one-off instantaneous change in period could occur. Next slide, please. Now, Eta Musca is a target I've been observing since I first started photometry back in 2011. Most of the data points on this graph are my own. Not too many other people seem to observe this star. It's quite a difficult one. What seems to be occurring here is that the orbital period seems to be oscillating between slightly faster and slightly slower in a sort of sinusoidal pattern. But it's not actually changing. What's happening is that the eclipsing binary is orbiting around the center of mass of a triple system. So there's a third, at least one more star, and in fact there's 3 other stars, but there's a third star that the eclipsing binary is orbiting around. And as that EB moves slightly closer to us or slightly further away, the light takes slightly longer or shorter to reach us. This is called the light travel time effect. Next slide, David. I've added just a pure sine wave to the data points just to draw your eye to what the data is doing. There are rigorous mathematical procedures for determining the long orbital period and the ellipticity and the inclination and the mass ratios of the triple system from an O-C diagram, but I'll leave that to the professionals to do. I've just added a sinusoid for illustration purposes. In the case of Eta Musca, the long period is something around 5.5 years. So I've observed a couple of orbits so far. The amplitude of the light travel time effect is about 8 1,000ths of a day, or about 11.5 minutes, which equates to about 1.44 astronomical units. So that's how far that third star, well, yeah, that's what that third star is causing, a movement of the eclipsing binary by that much. The error bars, you'll notice, are quite large, and the scatter of data points is quite large as well. And that's because Eta Musca is a bright and difficult target. The atmospheric scintillation is a problem because I have to use quite short exposure times. And since I'm observing from close to sea level, there's a lot of atmosphere between me and the target. Also, the period is quite long at 2.4 days. So eclipses stretch over several hours, but are only 8 100ths of a magnitude deep. So measuring the precise times of minimum is a bit challenging. And to make it worse, it looks like the light curve shape in the eclipses changes a little bit from eclipse to eclipse. And that might be due to, I don't know, star spots or hot spots on the surface where the material from one star is falling on the other. I'm not entirely sure what the reason is, but it all adds up to being a difficult target. But I'll keep observing. Okay, next slide. My final example is a star, an eclipsing binary, that the binary orbit is elliptical. And that elliptical orbit, the direction of the long axis of the ellipse is actually precessing around over multiple orbits. That line of the major axis is rotating around as shown in this diagram. This sort of precession is due in part to relativistic effects. So studying eclipsing binaries showing this sort of what they call apsidal motion, the precession of the orbital axis. Studies of these sorts of stars can provide a test of general relativity. We can also, well, sorry, they, being the professional astronomers, can also determine a mean internal structure constant for the stars, which can be compared with theoretical models of stellar structure to test those models as well. So this next slide, David, the star I'm talking about here is GG Lupi, which has quite an unusual observed minus calculated diagram, as you can see here. All the previous ones I've shown the primary eclipses and secondary eclipses showed the same sort of behaviour. But with GG Lupi, the secondary eclipse trends are the opposite of those shown by primary eclipses. So here I've plotted with open circles the secondary eclipses down the bottom, and with filled circles all the primary eclipses. From about 1985 through to 2012, around the 5,000 cycles, you can see it on the bottom axis here. So between 85 and 2012, the primary eclipses were progressively later than calculated, whereas the secondary ones were progressively earlier. But after 2012, those trends have reversed, and the two separate parts of the graph are coming back together again. We can measure the time it takes for the precession of the orbital axis to go through one whole cycle from these A-C diagrams. And I found a value in the literature from a paper published in 2005. They only used the data on the left of the 4,000 cycle mark there. So they only had a small part of the A-C curve to work with. And they reported a value of 101 plus or minus 4 years for the precession period. With the extra data that I've collected since 2012, we should be able to calculate a much more accurate apsidal period or a precessional period, but I haven't tried to do that. Again, that's for the professionals to do. Okay, second last slide. This sort of work has produced quite a number of papers. At the top, I've got the ones that relate to the stars I've talked about in this presentation, but there are many other, well, quite a number of other publications as well on other eclipsing binaries. Most of these have been in conjunction with Ed Budding, who, along with other people, have really supported the variable Stars South observers. So we are currently working on a paper about VV Orionis, which I showed you that light curve right back at the beginning. Regarding the annual times of minima papers, we have those listed at the bottom, starting with like a paper describing the 2015 observations, and then every year since then. You'll notice that there's nothing there for the 2021 eclipses, because I haven't, I've just taken over from Tom Richards in writing those, and I haven't finished it. So what I'll do is combine the 2021 observations and the 2022 observations into a single paper next year. Most of these observations are done by just a handful of observers. And as I mentioned before, we've got somewhere over 1,100 timings from over 200 targets. So we could certainly use more observers. So the last slide, David. So in conclusion, period changes of eclipsing binaries can be investigated using the tool I described, the A-C diagram. But we need lots of eclipses over many, many years to get a full picture of what's going on. We can use new observations of times of minimum and combine those with published data in the papers, or from looking at the light curves in archival photometry from various ground-based and space-based instruments. Southern eclipsing binaries are relatively understudied, so there's thousands of them down in the southern hemisphere yet to be properly investigated. Many brighter than 10th magnitude, so well and truly observable by quite modest equipment. A lot of these aren't or can't be observed by the professionals because they're too bright for their telescopes. So collaborations between professionals and amateurs are very possible, and co-authorship of journal papers can result from them. But as I mentioned, we could use a lot more observers. So if anyone's interested, please get in touch. So this type of research is very satisfying and very important. Thank you. We still have a few people in the meeting, so that's encouraging. I didn't scare too many away. Do we have any questions?
Sorry, okay.
No, you go ahead, David.
I would just like to pick up on what you said about RV Gruis, and it brings up points I want to make about several other stars. So, David O'Driscoll, may I share my screen briefly, please?
You certainly may.
Okay.
I made the settings on these meetings to allow anybody to share because I didn't think we were going to have much competition.
Okay. Can you see an Excel spreadsheet there
We can.
Yes.
with RV Gru?
Yes.
I can't see what you're looking at. So, okay. You showed a rather complex O minus C for RV Gru. And those data, well, I've got clicked on here a few that include my observations and Tom Richards. And when I first started observing it, it was all over the place, as you were pointing out. But since then, I haven't had time to do very much because since 2016, I've been concentrating on a set of stars where we've been observing not just the light curves, but also spectra with the ANU 2.3 meter telescope. So I actually have quite a lot of spectra and can do, we can get RV data for this particular one, but also several others. And that'll be important in trying to model the systems. And I haven't had time to do that because what I'll talk about next week is a particular set of targets that involve eclipsing binaries with pulsating components. But in fact, I do have a lot of spectra of stars that I've observed and you, Mark, have observed, and also Tom Richards. So several of the ones that I picked out from the VSS database, when I had time with the ANU 2.3 meter, I also observed them. So I haven't had time to work up all those spectra, but there are several of those stars where we can proceed with actual modeling.
Mm-hmm.
And that's going to be too complex for me. So that's where maybe Ed or somebody else who's experienced with the Wilson Divinity program could also use those data and help us to model them. Okay.
Okay, that'd be great.
Good. Okay, I'll stop.
Mark, this is Roy. Could I ask you, for those cases where you've got a miscalculation of the cycle number, what procedure do you use to correct those errors?
It's simply a matter of adding half a cycle or taking half a cycle off. I've thought about how we might be able to do it with a spreadsheet automatically, but I think it's probably better to look at the data, and it's very obvious when a step has occurred because
sure,
it's going to be 1/4 of the period. So if your O minus C value is approaching 1/4 of the actual period, say if it's a 1 day order period, if you find your O minus C value is getting close to 1/4 of a day, you know there's going to be a step as soon as it goes over that. And that's just the function of the way the Excel equation calculates the cycle. It's basically a rounding error.
Okay, so you basically look at the data and manually adjust the values.
Yes, yeah. So in my spreadsheet that produces the A-C diagram, I'll simply go into the cell for that particular calculation and add 0.5 or take 0.5 off, depending on whether it's increasing or decreasing in.
Right. Okay. Good. Thanks.
Anyone else? Okay.
I was just a bit amused, Mark. In your, I think it was V625 Karuni, there was a change in period, but it showed how well Murphy was working, because there are observations every, well, at least every couple of thousand days. In the earlier period, there are observations about that sort of period, that sort of frequency later, but there's a gap of 10,000 days just when the change occurred.
Exactly. And I thought I might be able to fill that in by looking at the archival photometry from ASAS. Unfortunately, it didn't have it. It's a little bit too faint.
Yeah, yeah.
So yeah, I'd love to be able to track down some data, but I'm not sure what other sources there are. There's I've tried getting, there's a South Pole, a Chinese observatory at the South Pole, which can get 6 months worth of data continuously, but they're not talking to me. I haven't been able to find anything. I don't know, maybe it's because I'm Australian.
Yeah, I'm sure that's right.
Yeah, it's unfortunate because the potential for that archival photometry for all sorts of purposes would be just phenomenal. But whether the data is not as good as they thought it would be, or whether they're churning out papers of their own, I don't know, but it would be very nice to have access. Yes, I would like to fill that gap in. So you're not looking too bad there. You're not suffering too badly from the COVID, Jeff?
I got home about 11 o'clock last night.
Right.
So I'm feeling better than I had been last few days. Yeah, it was a big pity. Norfolk Island's a beautiful place and lovely place to be stuck, except for the fact that when you're stuck there, you can't go out and enjoy anything. So, it was a matter of spending a week inside the unit. And that wasn't actually so much fun at all.
Well, I'll tell you, you were much better off there than where I was a couple of weeks ago. I didn't have to isolate, but I was in the Kimberley region of Australia. And there's only one place to isolate there. It's in a town called Derby, in a hotel that had its best years maybe 50 years ago. And the tour leader's uncle was stuck in there for a week. And so he dropped off a care package for him, but none of us wanted to get COVID over there during that tour, that trip.
Yeah.
Okay.
But thanks for stepping in, Mark, because I just was not ready to present today. I'm very, very close, but I've got some stuff I need to actually put together to just tidy up. And also I'm going to see if I can get a little bit more analysis done on that test data you gave me. I've already got some interesting stuff out of it, so if I can push a bit further, I'll have more to say.
Okay, excellent. Well, looking forward to that. Okay. All right, David, you wanted to...
Well, just a reminder that next Saturday we'll be doing the same thing all over again. Next week we've got Tom and David Moriarty. So please, same bat time, same bat channel. Hopefully everybody found the instructions that were being emailed to them through Eventbrite suitable. Arne and David, I will send you a separate email with all the connection details the night before, just so that you have them, just so that you're not looking for them. I've found that over communicating is a better process than under communicating. And if anybody can send me their slides, Ed, can you forward to me your slides so I can load them up? I'll convert them to PDFs as I usually do and load them up to the website. And Arne and David, the same thing for yourselves, just so that I've got them in case there is an emergency.
Okay.
Something on Dropbox.
For some of them I had overlapping, within one slide, two different things. So I'll just convert them all into single slides.
That'd be great, Dave.
Without the animations.
Yeah.
And I'd just like to comment that what I plan to do is a little bit different from what was written, because when I first put it in, the topic was what I actually wrote into the Variable Star newsletter in the most recent one. So what I plan to do is to say a bit more initially about using the ANU 2.3 meter telescope. And I've been able to do that mainly because of the project that originally I set up and just went along to people at UQ and said, I've got a lot of light curve data and it'd be really nice to get spectra. And Michael Drinkwater said, yes, and it'd make a good student project, write a proposal. So that's how it all started. And I've got quite a lot of spectra, as I just mentioned briefly there before with RV GRU, but several other contact or close eclipsing binaries that have been observed by Mark, by Tom Richards, and I'm not sure, anyway, one or two others in the variable star group, where I just looked to see what the light curves look like and whether it would be worth getting spectra. So what I'll do is just put a list of those up next week. And as I said before, I don't have time at the moment. We just published a paper with 3 of the 15 targets with pulsating components. So there's another dozen still to be written up. And that requires more time from me in actually analysing the spectra to get the radial velocity data, and then our Greek colleague to do the modelling on those. So we have lots of other targets where somebody else, we need help from a professional colleague to do the modelling on those contact and close eclipsing binaries. So I'll put those up next week as just part of the talk that I'll do then.
And Dave, if you want to update the abstract at all, that's fine. Just send it through to me and I'll update the website. Okay.
All right. I just need a bit more time to think about it. Yeah.
All right. Well, I think we've probably sat in front of our computers long enough today. We might call this particular session to an end. Thank you to all the speakers. Very interesting. If any of the people participating today want to invite other people to come along too, get them to contact David and he can then send on the information. We've got plenty of room. We can accommodate up to 100 people, so lots more. All right, thank you all. Thank you for participants and the speakers. Cheers.
Thanks, Mark, and thanks very much to David for assistance with the computing.
No worries.
Okay. Bye.
Bye all.
Thank you.
Bye.